In this video, we'll look at how to identify and distinguish between the different types of geometric isomers. Geometric isomers, which are often referred to as stereoisomers, represent molecules that have the same molecular formulas, their atoms are connected the same, but their three-dimensional structures are different. And so the first thing to do when trying to identify whether or not two compounds can represent stereoisomers or geometric isomers, look at how the atoms are arranged. In the case of these three examples shown, they all have 4 carbon atoms and they each have a double bond. Where that double bond is located is different. The very first molecule, the double bond is at the very end. So remember, we can number in both directions. So since that double bond is at the very end, this molecule would represent 1 butene. However, in the other 2 molecules, the double bond is located in the very middle of the compound. Whether we number from left to right or right to left, they both represent 2 butene. And so in the case of the 2,2-butene molecules, their atoms are connected the same. So they have the 4 carbon atoms with the double bond between carbons 2 and 3. But looking at them, they look a little different. So their three-dimensional arrangements are different. And so when you're dealing with alkenes, due to restricted rotation, and what that means is that we can't rotate that double bond freely without breaking it. And so one way that you can do this, you can try to put your fingers together. So put your 2 fingers together, your index finger and your middle finger, put them together. You can't rotate it without breaking. If you put your single fingers together, your 2 index fingers, you can rotate without breaking. That is what we're referring to when we talk about rotation versus restricted rotation. The double bond has restricted rotation. It can only bend so far before it breaks. Single bond, it can continuously rotate. And so due to this restricted rotation, certain alkenes can exist as a cis or a trans isomer. And so the first step when trying to determine what type of isomer you're dealing with, you want to look at your alkene and you want to locate the double bond. So determine exactly where that carbon-carbon double bond is located. Because depending on how the atoms are arranged around that double bond, we may or may not be able to determine whether it's cis or trans. If the carbon atoms of the double bond, so each carbon of the double bond, if it has exactly 1 other carbon and 1 hydrogen attached, we can determine whether or not it is a cis or a trans isomer. If it doesn't have 1 carbon and 1 hydrogen, so if it has more or it has less, we cannot determine cis or trans isomers. Once we have determined that each carbon has 1 carbon and 1 hydrogen, depending on how the atoms are arranged, we'll then identify whether it's a cis or a trans isomer. Cis simply means the same side. Trans means opposite sides. So we're either talking about both of the carbon atoms that are attached or both of the hydrogen atoms that are attached. They're either going to be both on the same side of the double bond or both on opposite sides of the double bond. So let's look at the examples that are shown. That first compound, that 1 butene. Again, we have to locate our double bond. So the double bond was located between carbons 1 and 2. So we have the carbon atoms of the double bond. Recall when looking at skeletal structures, you do not always see those hydrogen. They're present, but they're not shown. But think about VSEPR, the valence shell electron pair repulsion theory. This tells you that electrons want to be as far apart from one another as possible. Remember, every covalent bond contains electrons. So if I already have electrons pointing in this direction, have electrons pointing in that direction, the other electrons want to be as far apart and would be pointing in this direction. The same thing with carbon 1. I have the double bond to carbon 2. That's all I see. So I know that this carbon is going to have 2 hydrogens. So remember, carbon wants 4 bonds. So we're simply showing what those 4 bonds are. And so if we look at that, carbon 1 versus carbon 2. So these are where my double bond, these are the 2 carbon atoms where my double bond is located, between carbons 1 and 2. Carbon 2 has exactly 1 hydrogen and 1 carbon, but carbon 1 only has 2 hydrogen. So with this one, we cannot indicate cis and trans. The reason why, if we're looking at the hydrogen, on carbon 2, we have a hydrogen that is pointing down below the double bond. On carbon 1, we have a hydrogen pointing above, which will make it trans, but we also have a hydrogen pointing below, which will make it cis. So looking at this particular molecule, this is saying that it is cis at the same time that it's trans. So instead, we would indicate it as neither. Neither cis nor trans. If we look at the next molecule, so again, you want to focus on the carbon atoms where your double bond is located. So these are my 2 carbon atoms where the double bond is located. Carbons 2 and 3. I have a double bond. I have a single bond. So that carbon already has 3 bonds. So that means that it would have a hydrogen. Because that bond is pointing downward, this one is pointing to the right. This one was going to point up and to the left, as far apart as it can be. So this was the C that I wrote over. It looks a little sloppy, and I apologize for that. But you have a double bond to the left, single bond down below. Your 4th bond is going to be the hydrogen pointing in the upward right position. So now, looking at the double bond, again, we can look at this 2 different ways. So we can see that carbon 2 has exactly 1 carbon and 1 hydrogen attached. We can see that carbon 3 has exactly 1 carbon and 1 hydrogen attached. So that's good. That checks off. We can move forward. From there, we can either look at both carbon or we can look at both hydrogen. Since I already have the hydrogen drawn, I'll do those first. So the hydrogen to the left is pointing up above the double bond. The hydrogen to the right is pointing up above the double bond. They're both pointing in the same direction. So they're both above the double bond. This would indicate that they are on the same side of the double bond, which will represent a cis isomer. I could have done the same thing with those carbon atoms. So each point represents a carbon. So if I had looked at the carbon atoms, the carbon to the left is pointing down below the double bond. The carbon to the right is pointing down below the double bond. So again, it still indicates that you have a cis isomer. So whether you decide to look at both carbon or both hydrogen, they'll tell you the same information. But you want to make sure that you're looking at both of the same. So either both carbon or both hydrogen. The way you would indicate that when naming it, it would still be 2-butene. However, you would add to the very beginning cis 2-butene. That cis 2-butene tells that this particular molecule has 4 carbon atoms. It has a double bond between carbons 2 and 3. And the double bond is arranged so that those groups are located on the same side. So the name tells you everything that you need to know about the molecule, structural wise. So I'm going to just redraw the last compound. So again, we had the carbon. I'm going to just go ahead and show all 4 carbon. So our last 2-butene molecule. So again, we want to locate our double bond. So we have the double bond between carbons 2 and 3. We have a single bond to carbon 1. This one is pointing somewhat down and to the left. This is pointing down and to the right. This one wants to be far apart, so it wants to point up. Carbon 3, double bond pointing up and to the left. Single bond pointing up and to the right. The 4th bond will point somewhat down. So again, we want to look at either both hydrogen or both carbon. So I'll start with the hydrogen again. Looking at it with respect to the double bond. So here's my double bond. This hydrogen was in an upward pointing position, whereas this one was pointing downward. They're pointing in opposite directions. They're on opposite sides of the double bond. That would represent a trans isomer. I could have done the same thing by looking at the carbon. So I have this carbon to the left. I have this carbon to the right. So these are the 2 carbon atoms that are directly bonded to the carbon of the alkene. This carbon, so remember I said it was pointing down and to the left, so it's down below the double bond. This carbon was pointing up and to the right, so it's above the double bond. Again, it's pointing opposite directions, which would confirm that you're dealing with a trans isomer. A couple of things to note when looking at alkenes, specifically those where you can determine cis or trans. Your cis alkenes are going to have somewhat of a flattened appearance. So when you look at that molecule, the double bond looks as though it was flattened out. Your trans alkenes are still going to keep that zigzag going. So you still have the up, down, up, down. Another thing that I want to point out, when dealing with that trans alkene, because it still has that zigzag going, sometimes it's hard to see that this is above and this is below. You can do a little trick. You can take a pen, pencil, you can even use your finger. Put it across the double bond. Look to see whether or not those bonds are sticking on the same side of that pen or opposite sides. So in this case, those carbon bonds are on opposite sides. Or again, I can look at the hydrogen. They're on opposite sides. I could have done the same thing with that cis alkene. I'll go back to the original one since it has the carbon and the hydrogen. So if I put my pen over the double bond, I can see where both carbon groups were below. I can see where both hydrogen were above. So that indicates that we're dealing with a cis isomer. So that's one little tip when you're trying to identify cis or trans isomer. Another tip, this one applies specifically to the trans. So if you think that something is trans but you're not quite sure, take your pencil, your paper or whatever, and turn it until your double bond looks somewhat flat. So now my double bond looks flat. So now I can see, yeah, for sure, I have a bond up, I have a bond down. Or hydrogen, I have this one up, I have this one down. And so that will also confirm that you are dealing with groups that are on the opposite sides of the double bond so that you can determine that this is a trans isomer. And so the way you would indicate that in the name, again, at the very beginning. So that compound would still be 2-butene, but we would simply add trans to the very beginning. Remember, when naming organic compounds, you separate numbers from letters using a dash. So here we have 1-butene. We couldn't indicate cis or trans because carbon 1 had 2 hydrogen. So it would simply be 1-butene. Here we have cis 2-butene. We could indicate cis or trans because carbon 2 had 1 carbon and 1 hydrogen. Carbon 3 had 1 carbon and 1 hydrogen. Both carbon groups were pointing in the same direction, just as both hydrogen groups. So it represented the cis isomer. Here we have trans 2-butene. Still have those 4 carbon atoms in my longest continuous chain with a double bond between carbons 2 and 3. But now my double bond has groups that are attached to it that are pointing in opposite directions. So carbon 2 has exactly 1 carbon and 1 hydrogen. Carbon 3 has exactly 1 carbon and 1 hydrogen. And both of those groups on the opposite carbons, so both carbon and both hydrogen, are pointing on opposite sides of the double bond. So this is how you would go through and identify whether or not an alkene represents a cis or trans isomer, or even if it could possibly represent a geometric isomer. So again, locate your double bond first. Make sure that each carbon of the double bond has exactly 1 carbon and 1 hydrogen directly connected to it, and then determine whether or not those carbon groups or the 2 hydrogen are pointing in the same direction or opposite direction.